In this video, we'll cover the basics of multithreading in C++. Multithreading allows programs to execute multiple threads concurrently, which can significantly improve performance and responsiveness. We will focus on the creation and management of threads for concurrent execution. So, what exactly is multithreading? It involves executing multiple threads simultaneously within a single process. Each thread has its own call stack, but threads share the process's resources like memory. This enables concurrent execution, where different parts of a program can run seemingly at the same time. Multithreading provides several benefits. It improves performance, especially on multi-core central processing units. It allows for better resource utilization, responsive user interfaces, and parallel execution of tasks. To get started with multithreading in C++, you'll need to include the appropriate header files. First, include iostream for input and output operations. Next, include the thread library, which is essential for creating and managing threads, and also include chrono for the time-related functions. It's part of the C++ 11 standard. This standardized threading library works across different platforms. Before C++ 11, developers had to use platform-specific libraries like POSIX threads or Windows threads. Also, make sure that you are using namespace standard. Let's look at how to create a basic thread. First, define a function that you want to execute in a separate thread. In this example, the function thread function simply prints a message 5 times with a short delay between each print. Now, in the main function, create a thread object, passing thread function as an argument to the thread constructor. This tells the new thread to execute thread function. Call join on the thread object. The join method waits for the thread to finish its execution before the main program continues. This ensures that the thread completes its work before the program exits. Threads often need to work with data, so let's see how to pass arguments to thread functions. Define a function, such as threadWithParams, that accepts parameters. For example, an integer ID and a constant string message. In the main function, create thread objects and pass the required arguments to the thread function in the thread constructor. For example, to create thread T1, we pass threadWithParams, the number 1, and the string hello from thread 1. Arguments are copied by value unless wrapped with standard reference or standard constant reference for references. Call join on each thread to wait for them to complete their execution. Once a thread is created, you need to manage its lifecycle. C++ provides 2 primary methods for this: join and detach. When you call join on a thread, the calling thread, typically the main thread, blocks until the thread finishes its execution. Join must be called exactly once per thread. It ensures that resources are properly cleaned up and throws an exception if the thread is not joinable. Detach, on the other hand, separates the thread from the thread object. The thread continues execution independently, and there is no way to directly communicate with the detached thread. Resources are automatically released when the thread completes. Use detach with caution, as it can potentially lead to zombie threads if not managed properly. Lambda functions offer a convenient way to define small, inline functions for threads. You can use them to encapsulate a piece of code directly within the thread's creation. Here's how. First, define a Lambda function such as Lambda1 that performs a specific task. In this case, printing a message 3 times with a short delay. Create a thread object and pass the Lambda function as the function to be executed. You can also create threads with inline lambdas directly within the thread constructor. Lambda functions can capture variables from the surrounding scope using capture clauses, such as =sign for by value or ampersand for by reference. The C++ thread library provides several utility functions to help manage threads effectively. The hardware concurrency function returns the number of concurrent threads supported by the hardware. This is useful for optimizing the number of threads you create to match the CPU's capabilities. The getID function, which is inside this thread namespace, retrieves the current thread's ID, which can be helpful for debugging and logging purposes. You can pause a thread's execution using the sleep for function, specifying the duration in milliseconds or seconds. Alternatively, sleep until pauses the thread until a specific point in time is reached. In a multi-threaded environment, thread safety is crucial. A data race occurs when two or more threads access the same memory location concurrently, and at least one of the accesses is a write. This can lead to unpredictable and incorrect results. Consider this example where multiple threads increment a shared counter variable. Without proper synchronization, this can result in a data race, and the final counter value may be less than expected. Data races lead to undefined behavior and are one of the most common bugs in multi-threaded programs. It is highly recommended to use synchronization mechanisms like mutexes to prevent data races. To write robust and efficient multi-threaded code, here are some best practices. Always join or detach threads before they go out of scope to prevent resource leaks. Use standard mutex to protect shared data and avoid data races. Minimize the scope of critical sections to reduce contention and improve performance. Avoid creating too many threads and consider using thread pools to manage threads efficiently. Be aware of thread creation overhead and optimize thread usage. Use standard atomic for simple shared variables that require atomic operations. Consider using higher-level abstractions like standard async for asynchronous task execution. To further enhance your multithreading skills, explore advanced topics such as mutex and lock management, condition variables for thread synchronization, future and promise for asynchronous results, thread pools for efficient thread management, atomic operations for lock-free programming, memory ordering and memory models, and task-based parallelism with standard async. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.